Module 7, Combination of Loading Modes. So till now we have seen different cases of fluctuating stresses acting on components, and we have seen how to design the components for various fluctuating stresses. Now we have three types of cases. First one is when the load which is a single load, can be an axial load, bending load or a torsion load, is fully reversed. Then design of the component is carried out based on the SN diagram. Now second case is when the load again single in the sense it can be an axial load, it can be a bending load or it can be a torsional load, is fluctuating with a mean component sigma m and an alternating component sigma a. Then in these cases the design is done based on the failure criteria. By failure criteria, mainly the Goodman criteria or Soderberg criteria, which we have seen in the previous module. Now third case is when the load is a combination. Now the load is not a single, it's a combination. That is, it's a combination of axial load, bending load and or torsion load. That is, can be axial, can be a bending load or can be a torsional load. When such kind of combination of load acts, then how is the design done? Now in such cases where we have a combination of loading modes, what we do is we generate two kinds of stress elements. One for the alternating stress or variable stress, and one for the mid-range stress. One for the alternating stress and one for the mid-range stress or the mean stress. Now in this case, when we have a combination of loading modes, how to take care of the stress concentration factors, because the stress concentration factors will be different for different kinds of loading. In this case, we will apply the appropriate fatigue stress concentration factors to each stress. That is, the fatigue stress concentration axial will be applied to the axial stress, and the fatigue stress concentration factor for bending will be applied to a bending stress, and the fatigue stress concentration factor for torsion will be applied to a torsional shear stress. Thus we calculate the resultant axial stress, bending stress and torsional stress, and each of them will have a mean component and a amplitude component. Now when we have a mean component for axial load, bending load and torsion load, how to find the resultant mean component? The resultant mean component resultant mean component sigma m dash is found out using the von Mises criteria. In von Mises criteria, we have seen that when we have normal stress sigma x and shear stress tau xy, the von Mises stress is given as sigma x square plus 3 times tau xy square whole raised to half. Now the same principle is applied in this case of combination of loading modes. Here the resultant mean component and the resultant alternating component both are found out using the von Mises stress. Now suppose we have axial load, bending load and torsion load in our case. Then the resultant alternating component sigma a dash is given as Kf, that is fatigue stress concentration factor for bending, into sigma alternating component of bending plus fatigue stress concentration factor for axial loading into the average component alternating component for axial loading. This will give the total normal stress, this square plus 3 times the fatigue stress concentration factor for torsion into the torsional shear stress, or the alternating component of the torsional shear stress whole square, the whole raised to half. This will give the resultant alternating component. Now resultant mean component again will be given by the similar kind of relation, that is bending stress concentration factor into the bending mean value of the bending stress plus the fatigue stress concentration for axial loading into the mean value of the axial loading. This will be the normal stress component square plus 3 times the fatigue stress concentration factor for torsion into the mean value of the torsional shear stress, the square, the whole raised to half. So thus we get the resultant mean stress and resultant alternating stress when we have a combination of loading modes. Now finally what we can do is, another thing we can do is, once we know the resultant alternating stress and resultant mean stress, then we can use the Soderberg criteria, Goodman criteria, Gerber criteria to complete the fatigue analysis. And for the endurance limit, the suitable modification factor should be applied for the endurance limit, and the correct endurance limit has to be taken for the design. And knowing the alternating component and the mean component of the stresses, or the resultant mean component and alternating component, we can use the failure criteria which we have discussed in the previous module, mainly the Goodman criteria, Soderberg criteria, or Gerber criteria for doing the analysis, doing the fatigue analysis. In this case, now sigma a will be replaced by sigma a dash, and sigma m will be replaced by sigma m dash. Now this will be the new Soderberg equation, and similarly we can write for the Goodman criteria also. This will be the Soderberg criteria, and this will be the Goodman criteria. Similarly, we can use the Gerber criteria also for doing the fatigue analysis. The main thing in this combination of loading modes is that we have to find the resultant mean component and resultant alternating component using this relation, which are nothing but the von Mises relations. And once you find out the resultant mean stress and the resultant alternating stress, then we can use the failure criteria like Goodman criteria, Soderberg criteria and Gerber criteria for doing the fatigue analysis and doing the design of the component for fatigue stresses. So with this we come to the end of the chapter on fatigue. So we have seen how to design what are the different types of stresses which comes in the body. One can be a completely reversed stress, which we have seen in the earlier modules. When we have a completely reversed stress, we make use of the SN diagram, which is nothing but stress number of cycle diagram, and we can design the component for infinite life and finite life design also. For infinite life, the design criteria will be such that the stress in the component should be less than the endurance limit. And for finite life design, we know that for a given fatigue strength, what is the number of cycle which the component can withstand. Then we saw that the reversed bending endurance limit of the body of the material gets modified by many factors called the endurance limit modifying factors, mainly the surface finish factor, size factor, load factor, temperature factor, miscellaneous factor, reliability factor. So how we account for these factors we have seen in the previous module. So endurance limit get modified by these factors. Then we have seen when we have a stress concentration, like in places like rods and shafts where we have a sharp discontinuity in the surface, we have to take care of the stress concentration factor. The theoretical stress concentration factor will get modified into a fatigue stress concentration factor. Here the fatigue stress concentration factor depends on another parameter called the notch sensitivity of the material. If the material is very sensitive to notch, then the fatigue stress concentration factor will approach the theoretical stress concentration factor, and when the notch sensitivity of the material is very less, then the fatigue stress concentration factor will be 0. So that brings out a new parameter called the fatigue stress concentration factor, which has to be included in the endurance limit of the material. Now after that we saw that how to characterize the fluctuating stress. Like fluctuating stress, we have seen that any kind of a fluctuating stress can be represented by two main components, mainly the mean component and the amplitude component. And we have also solved some problem, and we have understood how we can find out the mean component and the alternating component for a given variation of stresses. Now when we have fluctuating force or fluctuating moment or fluctuating load which causes a fluctuating stress, you have the mean component and the alternating component. When we have these two components, how to do the design? We have come across different failure criteria like Goodman criteria, Soderberg criteria and Gerber criteria, and we have seen how to design the component based on these criteria. We have solved some problem and understood how to design the components based on these failure criteria. Now after that we came to the final module, in which we have seen what happens when we have a combination of loading modes, that is when we have a combination of axial, bending and torsion load. Now when we have a combination of all the loads, we have to find the resultant alternating component and resultant mean component using von Mises criteria. And once we find the resultant mean component and resultant alternating component, then we can use the failure criteria like Goodman criteria, Soderberg criteria or Gerber criteria to design the component. So with this we come to the end of this module on fatigue.